Hello everyone, welcome to my channel. So in this video, I want to talk about some more important distributions in probability. So in this video, I want to talk about Poisson distribution. So similar with the binomial distribution, which we just talked in previous videos. So Poisson distribution is also one important discrete distribution in probability. So here, the first is, let me give what is the definition for a Poisson distribution. So here, assume we have a timeline. So here, let's say we have the time between time 0 until time capital T. So this capital T can be any positive numbers. So for example, you can think this as 5, and you can think like maybe 5 days, 5 weeks, or 5 years, any time you want. And then what we want to do is, for this timeline, we want to divide it to several partitions. So here the partition is, we assume we have n partitions. So here, if we write down these n partitions, then what we will have, because the total length of this interval between 0 and capital T can be denoted as capital T. So that means the length of each sub-intervals here, the small partition here, it should be capital T minus capital T divided by n. So in fact, we can actually extend this to some more general situation. So for example, here we say this is a capital T denoted as time, and actually this can also be some like area or some windows or lengths or something like this. So these are all classical examples of what we want to use for our Poisson process or Poisson distribution. And then before we define the Poisson distribution and Poisson random variable, we need to talk about what is Poisson process. So Poisson process is an experiment. So it's a random experiment with some important requirement or properties. So this actually we need 3 properties. So the first one is the probability of one event in a subinterval tends to lambda times delta t. So here, what's the meaning for delta t? So you can think this delta t here is about the length of each subinterval. So this means here you can think this t, capital T over n, is our delta t here. So then the second of the property is the property of more than one event in a subinterval tends to 0. So that means in our timeline here, it means in each of this subinterval, we only have one event. And then the third one is the event in each subinterval is independent of other interval. So here, this is other subinterval. So here, what this means? This means if we have several similar events happen in each of this subinterval, they happen or not is only depends on itself, not depends on others. So maybe this one you think is a really complicated, like you have no idea what this means. So for example, let me give one example. So here we can see like in Canada or in one country, there is some earthquake in a period. For example, we think period of 10 years. Then if we divide this 10 year to some subinterval, so we say each of subinterval is 1 month, then what we think here, if we think the first requirement, it means for the probability of one event is happens in the separate interval. It depends on a constant times the length of this sub-interval. So for example, if we say like for 1 month, it means a constant number times 1 month. If the sub-interval is 1 year, then this means we use a constant number times 1 year. So in other words, this event will happen in one sub-interval. It depends on the length of our sub-interval. If the length is longer, then that means it's higher chance for this event will happen. So in earthquake, actually this is correct. Like if there is an earthquake in one city in 1 year, the probability of this will happen is larger than there is one earthquake happens in one specific month. And then the second one is the probability of more than one event in a sub-interval tends to 0. So that means here, if you assume like for one city, they won't have 2 earthquakes in 1 month, then if this is some common sense or something actually satisfies like our knowledge, then we can say, okay, this earthquake is satisfies the second one. However, if this is not, maybe it's not correct. But also this depends on the sub-interval, right? So if we divide this sub-interval to like 1 minute, so in 1 minute, then we can say yes, in every 1 minute there is only one earthquake in one city. So if we think about this, then the earthquake happens in a period of like 10 years in one city. It satisfies the second requirement. And then for the third one is the event in each sub-interval is independent with the event in another sub-interval. So that means like if like last year we have one earthquake, and then maybe this year if our sub-interval is 1 year, then that means this year there won't or there is a earthquake or not. It didn't decided by last year we have an earthquake or not. So based on this one, you can see the earthquake happens in a period. Maybe it's not a good example of the Poisson process, because generally we say if there is a large earthquake, like just last day, yesterday, or last week, then generally we say there maybe will several smaller earthquakes in the following days or following weeks. So that means actually for the third requirement, it's not that correct. However, if we think about some other thing, like if we think about somebody like give a phone call to our service line or service center, then this actually is a good example to Poisson process, because generally for everyone they will just call at 1 minute or 1 second. It only happens like if we set the length of the sub-interval longer, then of course there's higher chance the officer will receive a call, right? And also like because this phone call is come from different customers, so of course people will have a phone call at a specific sub-interval. It's independent with there is another customer call the service center in another sub-intervals. And also the probability of the more than one event will happen in one sub-interval is tends to 0. This is also correct. Okay, so this is our understanding of what is a Poisson process. So if we have a clear understanding of what is a Poisson process, then the definition of the Poisson distribution and Poisson random variable is really smooth. So here, if we have a random variable which defines as the number of events in one Poisson process, then this random variable actually is called Poisson random variable. And of course here we have a parameter as lambda. So you can see in previous requirement for our Poisson process, we also have lambda, right? So lambda is the lambda times delta t is the like the probability of one event happens in one subintervals. So here for this one, we also use the same lambda here, and the probability mass function here is defined as this equation. So we can see here, this is in the numerator, this is exponential to negative lambda times capital T, and times lambda times t to power x divided by x factorial. So this is a Pmf of our Poisson random variable. So here, of course, if we have the capital T is equal 1, then this equation will become much shorter. So we just plug in capital T equal 1, and this equation will be simple. So now let me give one explanation of why we have this Pmf of Poisson random variable look like this. So here for a Poisson distribution, because when we talk about the definition of a Poisson process, so actually we divided a length of the whole capital T to n sub-interval, right? So each of the sub-interval what we have, actually for each of them we have two possible outcome. So one is we have the event happen or the event not happen. So what Poisson we can do is we can set a small n as the number of sub-intervals, and then like the limit in calculus, we just set this n limited to infinity, and then you can think like when the n Bernoulli trios binomial distribution will, when n goes to infinity, this will approximate our Poisson distribution. Okay, so for when we cite n Bernoulli binomial distribution, then so for this binomial distribution, then we have some parameter, right? So for here, for a binomial distribution, we need two parameters. One is n. So here, because we assume this it have a n Bernoulli trios, and then we also have this p. So p is the probability of event succeed. So here, what is our p? This p is our probability the event is happened in one subinterval. So here, in the previous requirement of our Poisson process, we already say this will approximate to our value lambda times delta t. And here, because delta t is equal our capital T divided by n. So in other words, our p here is equal lambda times delta t equal lambda times capital T over n. So this is our value for our p, the probability of one event happens in one subinterval. So then, what's the next thing is, by the binomial distribution, we can use the Pmf of binomial distribution. So here I use f sub capital B to denote the Pmf of our binomial distribution. So this is, we have the formula, right? So the formula is this combination times x to power x and 1 minus p to power n minus x. So this means in the n Bernoulli trio, so we have x of them succeed and n minus x fail. So if we translate this to something related to the Poisson distribution, it means in our n subintervals, we have x of them is the event happen and n minus x the event is not happen. So now if we rewrite this to a equation here, so that means we use the definition of our combination to compute this. We will find this equation can be rewrite as a equation with this factorial, and also we plug in the value of our p into this equation. So you can find this equation will actually look like this. Okay, So now we have the equation of our binomial Pmf. And as I said, we can use the n-trial binomial distribution to approximate our Poisson distribution. So the method we can do this is we can set n goes to infinity. And in other words, the Pmf of our Poisson distribution, I denote this by f sub p. This function is equal to the limit when n goes to infinity of our f sub bx. Okay, so this actually is if we say one distribution can approximate the other distribution as n goes to infinity. In other words, this means this is a Pmf of this distribution can approximate the Pmf of another distribution when n goes to infinity. Okay, so then what we have is actually we have this limited will become plug in the formula for our Pmf of binomial distribution. Look like this. So then here there is something important. The important thing is what we will have. We will need to use some knowledge of our limited. So if we have the limited of this equation, so I won't do this step by step because this is a course of probability, not anything related to calculus. But if you have later you have some confusing about this, please leave the question on comments. So maybe I will explain this more carefully or in details for you. So the idea of this is here what we will use. We will use the 1 over n x and this one. So because our x is a constant number, right? So the idea of this one, this will goes to 1 when we have n goes to infinity. And then the second thing is if we have this equation as n minus lambda t over n to n power, so this will goes to the e to lambda t, e to negative lambda t. And then the third one is n minus lambda t divided by n to power negative x. So this actually will goes to 1 when we set n goes to infinity. So based on these three properties, actually for the previous limited, we will have this will approximate what we have here is a lambda t to x divided by x factorial and e negative lambda t. So this is how we can use a binomial distribution to approximate our Poisson distribution. Okay, so then about the important thing when we introduce a distribution is we should introduce what the mean and variance of this distribution. So here for the Poisson distribution, the mean and variance, we have if x is a Poisson random variable with the length of the total interval is a capital T, and then the parameter is a lambda. Then here what we have the mean, or say the expected value of our random variable is lambda times capital T. And the variance also can be denoted by sigma square, is also equation lambda times capital T. So in our previous videos about the geometric distribution or negative binomial distribution and hypergeometric distribution, in those videos I give some example of flip a coin, right? So at that time we find the mean and variance of those examples is equal each other. But in those videos, I said this is just a special case. In general, the mean and variance of those distributions is not same. However, here for Poisson random variable, no matter which example you choose for a Poisson random variable, the mean and variance is always same. because the equation, by the equation you know both of this formula are lambda times capital T. Okay, so this is my explanation of this Poisson distribution, and in my next videos I will start to talk about some continuous random variable and how we can describe a continuous distribution, and what's the most important or classical examples of the distributions. So please subscribe my channel, and hopefully I will see you in my further videos.